and move right on. Okay, molecular geometry is one of the items I put under the heading of molecular dynamics. And in the general idea of molecular dynamics, what's the purpose of the concept? One is to determine the character of a molecule. Molecules have not only not two-dimensional ideas on a chalkboard, but they have a personality, I like to think, and that's the chemistry of them: bond making, bond breaking, reactivity, physical properties, chemical properties, on and on. And things that govern these directly, as we've talked about, things like electronegativity, when we talk about electronegativity, that word is very important in your chemical education. That's number one. Number two, it applies to individual elements within a structure. Okay, so it's got a nitrogen in it, that has a certain electronegativity or an attraction for the cloud around it, or carbon, or oxygen, or one of the halogens, and that acts to change the nature of the chemical bonds. So this is individual elements. Then electronegativity, we look at bond polarity. Once we understand the idea of bond polarity ranges from non-polar, or even distribution of charge across the bond, and we'll talk more about that as we go through geometry, to a bond which has the electron cloud between the two nuclei skewed to one of the elements, calling more negatives and less negatives, called polar covalent bonds. And we looked at molecular polarity a little bit. You'll see more today. And the two words that go with this are symmetrical and asymmetrical. I'll put those up there. And what this means, if it's still fuzzy somewhat, symmetrical means the electron clouds are distributed around the molecule very evenly. And as a result, we have a non-polar system. So symmetrical would be non-polar system. Whereas asymmetrical means not an even distribution of electron cloud, and asymmetrical distribution leads to polar molecules. And again, we will talk more about that as we move through our study on geometry. We looked at some, let's see, I want to put in bond making, bond breaking. Bond cleavage is what it's called. It's homolytic if you have an even break in the bond. One electron goes with the others, and this is called free radicals. Or we have an asymmetric cleavage, and that's called heterolytic. This is homolytic cleavage. Forgot to put that. And then if a pair of electrons goes with one element, that is a polar cleavage or a heterolytic cleavage. And we'll leave one of the elements with a positive and another element with a formal negative charge, and that's ions, obviously, cations, anions, and that's a heterolytic. And as you go through your chemical education, you'll find the majority of the reactions you will study will be in the heterolytic cleavage category, and of course there's hundreds of them, but they're classified for easy work with them. Okay, we looked at, like I said up here, how to calculate formal charge. Which is a formal charge in terms of a full plus charge or a full negative charge, different from what we call partial charges. In the polar bonds, where the electron cloud is skewed to one of the elements, where it has a larger concentration of electron cloud around it, we call that more of a partial negative charge, and the other element in the bond would be uncovered somewhat, and we'll call it partial positive. And that is very important that you understand that, because you put in other compounds with positive negatives and they will react depending on the reaction you're trying to run. Okay, and we look finally at resonance. Now, resonance is strictly defined as a situation where there's more than one Lewis dot structure that can be drawn. The physical issue is one of the orbital structures will delocalize around the entire molecule, and we'll get on that extensively today when we get to the valence bond theory. But the last item in this list is molecular geometry. Now, what's the significance of this dynamics list? If you are a chemist and you are evaluating the reactivity of molecules for whatever your reason, this is a systematic approach to defining what that molecule will do. You look for elements with high electronegativities, then you look for bond weakness or bond strength, whether or not the molecule is polar or non-polar. A good example is water. It has a formula weight of 18. Methane has a formula weight of 12, 24, 16, so they're almost the same weight. But water is a liquid at room temperature and methane is a gas. Well, that's a result of the asymmetrical distribution of charge around water. It will form charges in one water molecule will hook up with the other and they stay in liquid form. And methane can't do that because it has no polar points. Bond cleavage, you have to consider how one bond substitutes for another. The trend in all chemical bonding is to produce a stronger bond. That's a fundamental. So if you could remember that, if nothing else, the trend or rules that are always come to you is the formation of a stronger bond. Where something comes in, if something's bonded, it'll replace that item to make a stronger bond. And typically it'll follow the heterolytic cleavage. Formal charge is a result of ionization of a molecule, and those play a strong part in reactivity. We're not going to beat that to death. Resonance makes the entire molecule more reactive. But when you get down to the last item, molecular geometry, the three-dimensional character of the molecule is very important in how other molecules can attack a given start now and identify the theories of molecular geometry. Hopefully is constructive like that. There are three theories of molecular geometry. One is called the it's an acronym, VSEPR Theory, valence shell electron pair repulsion theory, and I'll bring that back up here in just a second. VSEPR. The second major theory that is proposed in this is called the valence bond theory. And the valence bond theory is based upon the changing of the valence shell. It undergoes a change or hybridization, and then interacts with the other molecules that are coming in to bond. I'll show you how that works in just a minute. And then the third one is called the molecular orbital theory. In which we consider things like diamagnetic, paramagnetic properties of bonds, and whether or not they have an anti-bonding orbital or a bonding orbital. We will not have time to go through that. If you do need molecular orbital theory, it's pretty straightforward in terms of how to use it. Many years I've been in chemistry, I found that the VSEPR theory and the valence bond theory have been sufficient to meet any of the needs that I've had to deal with when it comes to molecular geometry. So we'll start with the VSEPR. When we begin your study of molecular geometry, the first thing you have to understand in picking out three-dimensional structures is that there is a set of what we call parent geometries from which all the derived geometries evolve. So number one is a term called parent geometries. And parent geometries will produce derived geometries. So what are the parent geometries? Well, linear molecules exist. Then we have a trigonoplanar. Tetrahedral. Trigonobipyramid. Octahedral. And a pentagon. Bipyramid. Okay, now at first glance these seem to be, gosh, I gotta learn a bunch of terms that are hard to remember. No, they're not, because these represent three-dimensional figures, and by the time we finish what we're doing today, hopefully they'll be pretty simple to understand. Now, in constructing molecules, we have a certain notation that we use, and it's called central elements and substrate elements. And the way I'm putting and substrates. And the central elements are generically represented as a capital A, and the substrates are represented as, say, a capital X. And so if we wanted to identify, say, a linear molecule, you would have a substrate with a central element with two substrates like this. You would have an AX2 molecule. And what happens is these X's will assume a position in space that minimizes repulsion energy. And what does that mean? Okay, I'll show you. X bonds to A, bonds to X. The bond structure are electron clouds. And of course, Therefore, the charge is negative. So in the arrangement, when X bonds to A and another X bonds to A, the position that they would assume by natural selection, so to speak, is 180 degrees apart. So this is 180 degrees apart. That would be the minimum repulsion energy position, and that's why these are called valence shell electron pair. These are each electron pairs in each bond, and they have a negative charge. So when the bonds are formed, they will repel each other to positions in space that minimize that repulsion energy. And so all of these have their empirical relationships that minimize that bond repulsion. I'll go down through these and put the empirical formulas, and then we'll move on and show you the structures. Trigonoplanars in AX3, tetrahedrals in AX4, so we'll have 4 substrates around the central element. Trigonobipyramid has 5 substrates around the central element. Octahedral has 6. And yes, pentagonal bipyramid has 7 substrates arranged around it. Okay, so you're given this problem. It says determine the geometry of this molecule. Well, it's one of those 7 that you just looked at. And so you have to find a way to define whether it's linear or bent or whatever. You'll see that this can possibly be a bent molecule. You'll see that in water. Water is a bent angular molecule. Well, anyway, to evaluate this for what its geometry is, there are 2 more terms you have to be aware of, okay? And that has to do with the bonding pairs. What are we talking about here? We're talking about bonded pairs. These are between 2 nuclei, say carbon and say hydrogen. That is one bonded pair, and that's of course electrons. And how do you tell how many bonded pairs? Well, it's real easy. There's no calculation here. Look at the structure, the formula. The subscript of the substrate tells you how many bonded pairs you have. So when we look at beryllium chloride, this indicates 2 bonded pairs, indicating as far as chlorine will hook to beryllium and another chlorine will hook to beryllium somehow. Now we don't know yet what that arrangement is going to be. Is it 180 degree bond angle, or is it a different kind of bond angle, bent, for example? Those are possibilities. And so what you have to do, now this is a calculation, is determine how many non-bonded pairs. So we've got the bonded pairs easy enough by looking at the subscript, so we're there with that. But we need non-bonded pairs. Electrons. Now these are also referred to as free pairs. Electrons. Like that. The number of free pairs, now this is a formula that's similar to that AVO octet minus valence over 2, but this time, now keep it separate, it's going to be valence minus substrate number over 2. We're going to figure a valence number, a substrate number divided by 2, and that'll tell us how many electron pairs, non-bonded pairs, okay? So for this molecule, the valence number is calculated in the same way we calculated in the AVO-PEC. You have a beryllium and 2 chlorides, okay? And so beryllium, if you look at its position on, this is one of the few that is really kind of outside the edge of the non-metals, and the rest of them will be inside non-metals. But beryllium has a valence of 2. So we have one element that has 2 valence electrons. Now, everything we're dealing with has to do with valence. The core structure doesn't change. And then we have 2 times 7. Okay? And it says 40, 50, 16. Okay? So that gives us a valence number equal to 16. Now, the second number you need is a substrate number. Now, that deals with the attachments only. Now, in the AVO Beck, we figured the whole octet structure with the bonded centers and everything at one time. But here you only take into account just what's attached to the central element that's given. So substrate number is how many substrates do you have? Well, here's 2, and that build up is either 8 or 2, and the only one that's 2 is hydrogen. So we'll see that show up. So chlorine's not hydrogen, so it's going to be an 8, like that. And so your substrate number in this case is 16. So you have your valence number, substrate numbers. Everybody okay with so far? I mean, I'm not trying to throw you any curves. Okay. Main thing is valence, of course, it deals with the outer shell that's available for bonding in substrates or however many things are attached, 8 or 2 on valence electrons. Now, the number of non-bonded pair is equal to the valence number, substrate number minus the valence number over 2. So we have 16 minus 16 over 2, and that gives us 0 over 2, and of course 0 free pair. Okay, now what you're after here is the sum of the substrate number and the valence number. So to define the geometry, you need the substrate number plus the valence number. I'm sorry. Sorry. Need the free pair and the bonded pair. My bad. Okay, geometry. Bad start. Geometry is the number of free pairs plus the number of bonded pairs. I'm sorry. So when we look at the calculation here, we have 0 free pairs and 2 bonded pairs right there, and so that gives us 2. Well, what does that mean? It means your geometry, your parent geometry is an AX2. I'll just bring it up here. And this comes out 2, you have an AX2 geometry. And an AX2 is linear. So we don't have any free pairs to influence the placement of the bonds, and so they would assume an X 180 degree bond angle here, and so it would be chloride bonded to beryllium bonded to another chloride, like that, and it too would have a 180 degree bond angle. Now I know that may be fuzzy to you at this point, but after you see me do it 2 or 3 and we get going on this thing, you'll see, oh, I see how to do it. It never fails. You'll be fine. Okay. Trihydride in this structure. So we need a substrate number and that's equal to a 3. That's easy enough. You just look at the molecule, okay? And you need the non-bonded pairs of electrons, and that's valence number minus substrate over 2. So we'll get the valence number is boron plus 3 hydrogens. Boron is group 3 on the periodic chart, plus 3 times 1, and that's 6. Okay, the substrate number is, well, we've got 3 hydrogens, and that fills up at 2, and that's also a 6. So the non-bonded pairs that we have is valence minus substrate over 2, 6 minus 6 over 2, and 0 over 2. And this one too has no free pair. But when we add the substrates, number of substrates and the number of free pairs together, the S plus free pairs, number of free pairs, we have 3 plus 0, no free pairs, and that gives us a 3, which means that our parent geometry for this molecule is an AX3. So see how I'm getting that? So it's going to be the substrate, this number is the number of substrates attached. Okay? Subscript, what I'm trying to say. Okay, so what does an AX3 look like? Well, it's trigonal planar. And it has a central element right here, and it looks like a 3-blade propeller in which you have 3 bonds that are 120-degree bond angles. And the substrates are attached in that configuration. And so you will see it's planar. And that's very important to understand. If you have an AX3 structure, it's going to be planar. So looking at it from a side view, you might see it more realistically in this context. And you can see the triangle nature of it right here. I'll move it up. So this is a molecule that has a boron in the middle and a hydrogen, and a hydrogen, and no free pairs. Okay? Now I'm going to show you how to get the deal with the 3 pairs. This is where the parent structure and the derived structure are the same. So you need to make note of that, and you'll understand it as I go through the next part. Parent and derived structure are the same. Okay, now just go with me on that for a second and you'll see what I'm, because every problem we solve like this is going to be calculating what the parent structure is when we add the substrate number and the free pair. This always gives the parent structure out here, and only the parent, and you'll do that for every one. However, you'll draw the parent structure and you'll have some bars in here that will just be electron pairs, and I'll show you. Stannous chloride, for example, SnCl2. So 10 is called also stannous in there, and as you look in the periodic table, you'll find it in group 4 right here. So it has a valence number of 4 when we start working with that one. So here, you don't know whether it's linear or whether it's something else. That's the point I'm trying to get you to understand here. It could be a linear and it could be a derivative of a trigonal planar, because you have 2 or something even different. Okay, so we want the valence number. Excuse me. I've got so many terms running around. Substrate's easy enough. We need 2 things, substrate number and the number of free pairs, and then you calculate it. Substrate number is 2. Okay, so that's easy enough, right? Okay, so now our free pair, non-bonded pairs is equal to valence, substrate minus valence over 2. So to get the substrate, the valence number, that's 10 plus 2 chlorides, and that's 1 times 4. That's the valence of 10. I just showed you that on the periodic chart. Everybody okay? That's just number under group 4. Nothing complicated. Okay, and then The halogens are valence 7. 2 of them 7 is 14, 56, 7, 18. So I have an 18 valence number here. And so now I want the substrate number, which is 2 chlorides only. So you don't figure an octet number, you figure only the attachments. And when that one's bonded, it's going to be 8 electrons. It's either 8 or 2 in the substrate. And when we used hydrogen, we used 2 there. And so that's 16. So now I can take this, well, valence minus substrate. Turn that around. I'm not thinking straight. Valence minus substrate, this one up here. So the valence is 18, big number minus little number. 16 over 2, that's 2 over 2, and that equals 1. So that is one non-bonded pair with this molecule. So when we look at the number of bonded pairs, then add that to the non-bonded pairs, we get the parent structure. Okay, so the bonded pair is 2. The non-bonded pairs we just calculated is 1. And you add those together, you get a 3. Well, that means the parent is an AX3, trigonal planar parent. So when I draw the trigonal planar structure, I have a central element and a bar, bar, bar is 120 degrees apart. However, what kind of attachments do I have? I only have 2 things bonded, and that's a chlorine on here and a chlorine over here. But what do I do here? That bond is a non-bonded pair. That's where you put that extra non-bonded pair. And so when you name the geometry of this, it's going to be a derived geometry from the parent. See, this is the parent, and this is a derived geometry. The derived geometry is in terms of the attachments only. So when I draw out the attachments between the chlorines and the central element right here, that shows me a bent geometry or a bent angular geometry. So it is evolving from the parent structure here. And so when we talk about geometries, we first begin with the parent geometries, and we look at linear and an AX geometry, AX2 geometry, and that is X here. Okay, that doesn't have any derivatives. Okay, so if you look at this handout I gave you, you'll see that right here. Now we haven't gotten to the other geometries, but here are the derived structures. You see there's a bunch of them over here, and these evolve from the parents. Here's the parent structure. So basically, if we, in the beryllium dichloride that we did a few minutes ago, that's as far as you can go with a AX2. But an AX3, here we've got beryllium trifluoride. You want to do that one, or boron trifluoride, or boron trihydride. Here's a bent angular. Here's another bent angular, because one of the electron pairs in here is a non-bonded pair. And so we have to put all electron pairs. That's why it's called the VSEPR theory, electron pair repulsion. And so you have to draw out the parent first, and then you put in your 2 attachments, and then one of bond, anything left over accommodates the electron pairs. So you might put a note in here, electron non-bonded pair. You might put non-bonded pair right there, and it came out of the calculation. So trigonoplanar is certainly an AX3, but we have the parent structure and one derived structure. And this is the parent is trigonoplanar, but the derived structure will be a bent. It's called bent angular. Some people call it bent angular, but we just call it bent. But one of the bars in here is a non-bonded pair. That's bent, not bend, bent. Okay, so we've got several more molecules to go through, and you'll see how this begins to get a little easier because it's so. Okay, AX4 molecules. Well, here's some examples of some AX4 molecules. CH4 and H3 and H2O. I'm going to move these over a little bit if I could. Let's see, let me put it over here. CH4 and H3 and H2O. Now, what do we need in order to define its geometry? Well, that's what I'll put over here on the left. We need to get the substrates. Number, and then we need to get the valence number. Free pair, non-bonded pair. I don't know why I'm having trouble getting my brain in gear this morning. Non-bonded pair number. Okay, move that over a little bit more. Well, it's easy to get the substrates. The number of substrates is whatever's attached. So we have 4 substrates attached, we have 3 substrates attached, and we have 2 substrates attached. So you can see the pattern in terms of substrates, where your non-bonded pair is your valence number minus the substrate over 2. All right, and this one we'll find the valence is 4 and 4, that's 8. We got 4 for carbon, 1 for each hydrogen times 4, and so that's 8 is the valence number. Substrate number, when hydrogen's filled, is 2. So 2 times 4 is 8. Divided by 2, and so for this one, we have a 0 number of non-bonded pairs. Did everybody kind of follow me? I kind of didn't pick those out, draw them all out. Carbon's 4 valence, hydrogen's 1, and we have 4, so 4 and 4 is 8. So that's 8 valence number minus substrate number, 2 times 4 is 8. So the number of electron pairs and per parent is 4 and 0 is 4. So the geometry, let's go parent first. Parent geometry is an AX4 tetrahedron. The derived geometry is an AX4 also. It doesn't have any free pairs, okay? And there's one little notation I didn't show you a minute ago, but it's easy. Okay, now let's repeat for the ammonia molecule right here. So the non-bonded pairs, of course, are valence minus substrate over 2. Okay, so the valence for nitrogen is in group 5 on the periodic chart. Hydrogen's 1, that's 8. So I have 5 plus 3 is 8 for my valence. Now the attachments when hydrogen is full is 2. Anything else would be 8. So 3 times 2 right there is 6. So 8 minus 6 over 2, and that leaves me 2 over 2, or 1 free pair. Now the total free pairs and substrates pairs, bonded pairs, okay, total out to 4. Well, the parent is AX4, but we have a non-bonded pair. So the derived geometry is based on an AX, 3 attachments in here, and 1 non-bonded pair, like that. Now, they're always started with the tetrahedron. So you got the central element, and you draw a vertical bar, and I like to draw one kind of at an angle like that, and then another one slightly out longer angle like that, and then come over to the other side right here. That's a tetrahedron. So come straight up and down, left, right, and then kind of an angle like here. And here are your 4 hydrogens attached here. And so that would be, your geometry would be tetrahedral. Ah, wrong place. And tetrahedral is both the parent geometry and the derived geometry, so they're the same in this. Now, when we do an AX3E, we have to account for all 4 electron pairs, and we draw the same thing. That is nitrogen this time in the middle, and then we come off to the sides, and then one angle out like that. But this time, I only have 3 attachments, and this one up here is going to be a non-bonded pair. And so when I look at the geometry of this, it's pyramidal. Like that. See that? So when I stripped out the bonded items in here, you can see the pyramid in there. The non-bonded pair is not taken into the name of the structure, and you can see pyramidal in there. But in order to get to the pyramidal, you have to find the non-bonded pair in the structure. Now the water will do the same thing. It'll show its parent structure will be a tetrahedron, but we'll have 2 non-bonded pair and 2 bonded pair, which will leave us with a bent structure. So let's go back over here a little bit to, we've got 2 bonded pair, so we need a valence minus substrate over 2. Well, the valence of oxygen is 6. Hydrogen's 1, and we have 2, so that's 8. Okay? And then your substrates, we have 2 substrates hooked on, so that's 2 times 2 is 4. So 8 minus 4 over 2 gives us 4 over 2, or 2 non-bonded pairs right here. So we have 2 bonded pairs, 2 non-bonded pairs for 4 electron pairs total. And then put a help electron pairs. And so now this defines how you put the parent together, but then you put in the bonded pairs and electron pairs, and so we have an AX2E2 is the empirical relationship, that is the notation that's used anyway. AX2E2 for, well actually it's AX, I'm getting this mixed up, AX4 parent in that order, and then its geometry is AX2E2, and you'll find out that's bent. This one is pyramidal, and this is both parent and pyramidal. So we come down here and we draw our tetrahedron again like that. Here's the oxygen in the middle, and we'll attach a couple of hydrogens, and we'll leave these 2 non-bonded pairs. So the AX2E2 is a bent geometry, and again, just to refresh this, only the attachments will define your geometries. Since everything's bonded out here, you can see the tetrahedron, and this is pyramidal, and this one would be again bent in that way. Okay, here of parent structures. So here we've done the linear, and we got the AX2, and then we did the trigonal planar right there, and the bent angular. See, it has 2 attachments and 1 non-bonded pair, and here we have a tetrahedral parent, and then we have a pyramidal. There's your 3 attachments in electron pair. Here's your binangular, 2 attachments and 2 electrons. And here's some examples over here that you can do. Now I'll show you how to do the ions here in a few minutes. Let's get through the others. Now we move to a trigonal bipyramid, and it has molecules AX5, 5 attachments to the central element. So that's a unique geometry that departs these molecules. Next 3 examples here depart from the octet rule. So you'll see 5 times 2, that's 10 electrons attached to the central element in there. So we're going to start with PCl5 and build. Now I want to show you how to draw it first, and then we'll go into the determination of bonded pairs and non-bonded pairs in a second. A trigonal bipyramid, start out with what I call a lazy triangle. Get a little bit more angular than that. There and there. See, kind of a obtuse angle, and then bring this back to the point. Now there's a triangle right there. Go straight up out of the center here and straight down out of the center like that. This is your central element right here. Change colors for the benefit of the interest. So we've got a central element right there, and then you will have bonds go into the central element right here. So here, here, and here, here, and here are either bonded pair, electron pairs, non-bonded pairs, or whatever. And then you draw your model around the bonded. If we had, say, everything bonded out here, you'd have 5 bonded pairs like that. Well, you could see, hopefully, a bipyramid. The ammonia was pyramidal, but that's a bipyramid. Here, yeah, you can see these okay. Here's your linear parent right here. Here's your trigonal planar right here. Here's your tetrahedron we just played with. Try to remember that 109.5 bond angle in there. When everything's bonded out, it's 109.5. But if we substitute or leave something off, that bond angle will change. I'll get to that toward the end of this. Here is your, see how you have the little triangle in the middle, and here's your central element, and you have your electron pairs at the points of that trigonal bipyramid. Then here you go. Here's an octahedron right here. You got a square in here, and then you'll have a square pyramid, and all the way around the structure. There is a 5th one, a pentagonal bipyramid. I'll draw that out when we get to it. But we'll only look at the parent on that, not the derived structure, and work out the PCl5. Okay, so we want to start with PCl5 here. So you got a substrate. You got 5 substrates. Okay, so attachments, and so that means you have 5 bonded pairs. Okay, so that's attachments. Okay, then we want to get the free pair, and of course that is, well, just put the formula: valence minus substrate over 2. Well, let's see, the valence is phosphorus plus 5 chlorides. Phosphorus is in group 5, right under nitrogen, and so it has 5 valence electrons. Chlorine, group 7, we have 5, 35, 40 is our valence number. Okay. Our substrate number, when all of the chlorides are bonded out, each chloride has 8 electrons, and so that would be 5 chlorides, so to speak, and 5 times 8 is 40. And so with these we can get the free pair, if any, 40 minus 40 over 2, and this has 0 free pairs. So everything revolves around this. So substrate plus free pair equals 5 plus 0, if you will, just to make it clear. 5 bonded pairs, all we have, and which gives you an AX5 geometry, no free pairs in there. Everybody see okay? X5. So to draw this molecule, we would essentially have this structure, bring it back down a little bit, right here. And we draw the lazy triangle, put a phosphorus in the middle, and then attach the chlorides all the way around. Everybody kind of good with that? And it's pretty straight. You will not have to draw these on your exam, obviously, but in order to figure them out, you kind of have to have them on scratch paper somewhere. So SF4 has substrates of 4 bonded pairs on there. So you know what your X is going. Well, we can put it X if you want to. It's going to have an X subscript 4 on there. And now all we have to do is get the E part on there. Does it have any non-bonded pairs? So really what we're saying here is this molecule is an AX4, but the question is, what's the E out here? Is it E1, E2, E3? If it doesn't have, if it's 0, that's a tetrahedron. Remember? If it comes out AX4, it's a tetrahedron. And of course we're following the description here on the table. Okay, so define your non-bonded pairs, free pairs. Valence minus substrate over 2. So our valence is sulfur plus 4 fluorides. Sulfur's in group 6 on the periodic chart, plus 7 for fluoride, the halogen group, number 7. 34. 7 to 4 is 28, 29, 31, 2, 3, 34, yeah. Okay, so substrate number, we have 4 fluorides. So it's 4 times 8 attachments. It's 32. So now we can calculate the non-bonded pair and add them to the bonded pair, and we'll know what the parent is. Okay, so that is 34, 32, 2, 2 over 2, or 1 non-bonded pair. Okay, we got 4 bonded pair and 1 non-bonded pair. So the parent structure is an AX5. 4 bonded pairs, 1 non-bonded pair. But the geometry has to do with only the bonded pairs. And so that's an AX4 with 1 non-bonded pair. So that's the script or the empirical relationship. So since it's a parent structure of trigonal bipyramid, we want to draw our little triangle, and 1 to the center and 1 out here, and then put bars from the center outward like that. Now this is rule 1, and there's only one rule here in placement of your non-bonded pairs. In working with the trigonal bipyramid, the first electron pairs will go in the plane of the triangle. So your first electron pairs will go, if you have an E2, you would put 2 non-bonded pairs, but everything starts in the triangle. Now, in the next AX6, the octahedral parent, you will start with the electrons going in above and below the plane. Now let me, again, what I'm trying to say here is your bipyramid, and say we found out that this molecule had 1 non-bonded pair. Well, you'd put it in here first. But if you made a calculation over here, if you can see the triangle in here, This is an octahedral. Well, your electron pairs will go above and below that plane when we get to that molecule. So kind of keep in mind that if you're working with the AX5 system, free pairs go in the triangle first. If you're working with the AX6 geometry and systems in that, they will go above and below, and then they would enter into the plane. Okay, back to this one. So if we only have one non-bonded pair, so I'll just pick out one of the bonds there. Everything else is a bonded pair. So when I draw the graphic around this one here, you see what, and you can see in the handout that I gave you, this is called a seesaw geometry. If I took that and turned it on its side, it would look like a seesaw on a teeter-totter on a fulcrum, like that, and it would have its bonded here, and there's your central element, and you have AX4, and it would look like that. So you can see it in probably better in that second handout I gave you. Here's that SF4. You see how they draw that? But it comes out of the trigonal bipyramid, and you see it's kind of a seesaw laid on its side. The next one will be T-shaped, and then we'll go to linear. And so here's some of the examples that we'll work. Now, when you look at the formula like this, what should go through your head? Well, you know, just off the cuff, that could be a trigonal planar, or it could be a tetrahedral derivative of one free pair, or it could be a trigonal bipyramid with two free pair. So you have to make that calculation. All you know right now is there are three attachments to the central element in the structure. So the number attachments, so to speak, is 3. So we know we've got an AX3 geometry to start with. But the question is, do we have any electron pairs? Okay. So now, valence is chloride plus 3 fluorides is equal to 7 plus 3 times 7 is 28. Substrates are 3 fluorides. 3 times 8 is 24. And free pairs, valence minus substrate over 2, 28 minus 24 over 2, 4 over 2, so we have 2 free pair. 2 free pair and 3 bonded pairs. So the parent is equal to 3 plus 2, or AX5. And the geometry, when we finish with this, is an AX3E2. And we draw our lazy triangle like that, straight up and down. Put our bars in for bonds, and we start putting there's the central element. Where do the electron pairs go in this? Where? Into the plane. Okay, so. And then everything else is left bonded. Oh, sorry, that was not bonded. And so, if you look at this, the graphic on this now, just goes straight through and is a T shape. Center, bond, 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 and you have your non-bonded pairs over here, and so that's a T shape. So once you get the structure drawn, you can figure out just from the mental imaging of what's going on. Okay. So we know it's got substrates or two bonded pairs. Okay, and your free pair is valence minus substrate over 2. So the valence is xenon plus 2 fluorides. Well, xenon's number 8, so that's 8 valence electrons. So 1 times 8 plus 2 times 7 for group 7, it's like 22. So your substrates, we have 2 fluorides attached. 2 times 8, 16. And so free pair, I'll put it back up here, 22 minus 16 over 2, that's 6 over 2, or 3 free pair. So now this molecule is an AX2E3 geometry, right there. But it's based upon 3 plus 2 is 5, so its parent is an AX5, which is the trigonal bipyramid, like that. But we have 3 free pair, and these 3 free pair will go in the plane, and then the central element, and your bonds are here, and this becomes your geometry. AX2E3 is linear. So you have your fluoride, then you have your xenon, then your fluoride right here, and then you have 1, 2, 1, 2, 1, 2. So you have 3 non-bonded pair around the central element in the plane of the triangle, like that. So this gives you an idea of all of the possibilities for that one. So we'll do the octet real quickly here. I think you'll find, and I can do some ion structures. There's another ion in this one, but okay, this is an ion, polyion carrying a negative charge. The negative charge comes from the addition of an extra electron. So that extra electron has to be added in the valence number, just like we did in the AVOPEC. We add 1 electron. So in this you have your substrate, you have 2 bonded pairs. Your valence number is an iodine plus 2 chlorides plus 1 electron. And that extra electron is for the negative charge. And so we have 7 plus 2 times 7 plus 1, 22 is your valence number. Substrate number, you have 2 chlorides, that's 2 times 8 is 16, so free pairs is now 22 minus 16 over 2, 6 over 2, or 3 free pairs. So you got 2 bonded pairs, 3 free pairs, so that would give you a parent of AX5 and a geometry of AX2E3. So you start out with your trigonal bipyramid, getting sloppy, I know, like that. And so it's geometry, 1, 2, 3, and there are your chlorides. And you bracket that, put a negative out there, like that. So while I didn't do anything radically different other than put brackets around it to show it's an ion and put a negative charge on the structure. That's all I did. Okay, now the octahedral geometry is an AX6 parent. Now to draw one of these, draw what I call a lazy triangle, not a lazy square, parallelogram, if you will. See how I did that? And then 2 bars straight up and down, as shown here. That'll be your central element, and your attachments, if they occur, are to the points. So that's an AX6 geometry, and it's called an octahedron. And you can hopefully see the octahedron as I draw it here. It's 4-sided down to there. I've got to get that one right there. Like that. Now, free pair enter in the above and below the plane of the triangle. I mean, of square. So SF6 would be our first example. Okay, so we look at this as an AX6 possibility, or AX6 with free pairs, you know, like that. Well, your number of substrates or bonded pairs, your number of bonded pairs, of course, is 6. So your free non-bonded pairs is valence minus substrate over 2. Valence is sulfur plus 6 fluorides. That's 6 plus 6 times 7, 48. Like that. Your substrate number is 6 fluorides, 6 times 8, and that's 48. So we have 48 minus 48 over 2, or 0 free pairs. So we got 0 free pairs, 6 bonded pairs, 6 plus 0. And so these two give us an AX5 parent and geometry. So this is both the parent and geometry. So here is your SF6 right there. Everything bonded out, sulfur in the middle and fluorides attached all the way around. I know we need to take a break, guys. Hang on. And I get through this, then we can come back and do the valence bond, and we'll be out of this. BRF5, all better. AX6, you're right. Well, make a long story short, this one's going to have 1 free pair and 5 bonded pairs. So what we're looking for is to prove an AX5E non-bonded pair in here. Well, you've got 5 attachments, so the bonded pair equals 5, and so the non-bonded pair has got to be 1 when we finish this. So the valence number minus substrate over 2. Well, I've got 5 7s, another 7 here, 7 6, 6 times 7 6 42 minus the substrate. 5 to makes 40. 5 to makes 40 over 2, and I hope I didn't lose anybody because I'm jumping over all the little notations. So we have 1 free pair, and we have 5 bonded pair. So that gives us the AX5E. And so when we draw this molecule, we want our free pair. I like to put them on the bottom down here, and then make the attachments above the plane, and then draw your graphic. That, oops, I forgot one of my bonds right there. And this is called a square pyramid from an octahedral parent. I'm going to jump to, let's see, there's a ICO4 in here. And this one also is negative. So we have bonded pairs is equal to 4, and it's going to come out with AX4E2 when this one shows up. So it's going to be a square planar when we finish with this one. Let's see. Square planar because electrons go above and below that square in the middle here. You can see that square plane in here. Okay, so number of free pairs is valence minus substrate over 2. Well, a valence number for this is, well, 5, let's see, 7 to 4, 7 to 5, 35, 36 plus 1 electron. So I have 36, and then 4 to 8 is 32 over 2, 4 over 2, or 2 free pair. Like that. So our geometry now is an AX4E2. And so when we draw this one, we want to put our free pair above and below the plane, and our attachments, there's the central element, iodine, and I'll change colors just for reference. So it's pretty easy to see in there the square planar in the planar geometry. Now the next one would then enter the electron pair in here and would become a T-shaped. So if you dropped off one more, it would put it in and become T-shaped. It's not an example in here. You have an XEF4, try that one. It's also a square planar. Now draw out the pentagonal bipyramid and just make reference to that. That's all. We're not going to do any derivatives. Okay, pentagonal bipyramid. What's a pentagon? It's a 5-sided structure. So we went from a triangle to a square, now a 5-sided structure. If I can draw this without making a big mess. That. Here. Then you have that in the center. Here. There. I believe the F7 does exist. And it's easier to prove with the valence bond theory and like that, but that's called a pentagonal bipyramid with an AX7 parent. And it has several derivatives, but we're not going to deal with those in this course. You check it out.
That's supposed to be 6 for the parent?
Probably. Parent is AX6, yes.
So
That's
the parent is you add the
It's the
bonding and the free.
octahedron.
Yes.
Parent's octahedron AX6. But square pyramid is one free pair on the parent. Does that make sense? Okay.